Even if you are comparing carbon selenium, carbon tellurium is the most pi accepting. But if you ask a question why, and therefore if this is carbon monotellurium is the more pi accepting ligand, why so much of studies have not been done? This is because of the stability or the difficulty in preparing the carbon monosulfate, carbon monoselenium or carbon tellurium, and that is the problem. Whereas a carbon monoxide is readily available. And the karanathanala we have been done with so much of compound, but others are a bit difficult to prepare, so we could not be able to get it. Okay, so இதுதான் பார்த்துட்டு இருந்தோம், கடைசியா முடிச்சோம். ஸோ ஏதாவது டவுட் இருக்கா பிஃபோர் ப்ரொசீடிங்? ஏதாவது படிச்சுட்டு இருக்கீங்களா? எனி டவுட்? ஏதாவது ஒரு ப்ராப்ளம் ஒர்க் பண்ணிட்டு இருக்கீங்களா? ஏதாவது டவுட் இருக்காப்பா? Okay, fine. I hope the PowerPoint is visible. So shall we start for the day?
Yes, sir.
Okay. So the next ligand. So what we actually discussing about the isoelectronic species with respect to the carbon monoxide. If carbon monoxide can act as a very good pi accepting ligand, what about the other isoelectronic species like carbon monotellurium and the thing? Now we moved one more step ahead, Cn minus. So those Cn minus, so this is interesting definition kind of thing. You have a metal carbon bond in the metal cyanide, we won't call them as an organometallic compound. Whenever you have a metal center attached with only with the cyanide 6 times or 4 times, or the homoleptic cyanide complexes are not even called as the organometallic compound. So, but if you compare the the molecular orbital diagram of your Cn minus, it's very much similar to that of your carbon monoxide, having a pair of electron in the sigma orbital and having an empty pi star orbital. But still, so therefore, if you say for the given definition, what we said about organometallic, initially we say metal carbon. Yes, we have a metal carbon bond, and you should say there is a pi accepting ability should be there. Yes, of course, Cn minus have a empty pi star orbital, therefore the pi accepting ability is also there. But still, if a metal center bound only with the cyanide ligand, we won't call them as an organometallic compound. Why? Because the cyanide ligand, the cyanide Cn minus, do not have the ability to stabilize the metal in lower oxidation state, whereas all your carbon monoxide and any other organometallic ligand will try to stabilize the metal in lower oxidation state, and that's the main problem which we are facing with respect to the cyanide ligand. They will always have to keep the metal in the higher oxidation state, whereas it doesn't have the ability to stabilize the metal center in the lower oxidation state. Therefore, when you have a Cn minus as a ligand, we won't call them as we don't call them as an organometallic ligand. Rather, we say simply it is nothing but a simple coordination compound. Simple coordination compound, I mean talking about in terms of the coordination chemistry. So remember, you have a metal cyanide. In case of metal cyanide, you have a metal carbon. You also have a empty pi star. Therefore, Cn minus has the ability. If you are asking the quality wise, they are very poor, poor pi accepting nature. But definitely, Cn minus is a very good. I mean, Cn minus is a pi accepting ligand, but the ability is low. That's a different story. Though it is satisfying the metal carbon bond and pi accepting ability, we won't call them a cyanide ligand as an organometallic ligand only because it doesn't have the ability to stabilize the metal in lower oxidation state. So that's for any metal complex only with the cyanide. We don't need to worry about the organometallic property. We just follow only the coordination chemistry thing. Okay, the same way, if instead of having a metal cyanide, we also have isocyanide. These isocyanides are quite good. They have a metal carbon bond. They have a pi accepting ligand. Therefore, it is actually referred as the organometallic compound, and it is also a kind of a pi accepting ligand, which we can evidence from the stretching frequency. Therefore, there is no problem. Cn, the isocyanide NC is found to be, we can call them as an organometallic ligand. But in general, most of the cases, the isocyanide will be acting more like a sigma donor ligand, more like a sigma donor because of the negative charge. They tend to be more like a sigma donor, but a kind of a very poor pi accepting ligand. And therefore, whenever a metal complex in need of a sigma bonding ability, we always use the metal isocyanide, not not the other way around. Therefore, metal isocyanate, we can still call them as an organometallic ligand. And then we move to the important class of the organometallic ligand, nitrosyl, that is called the nitrogen monoxide. Nitrogen monoxide, if you count the total valence electron, nitrogen from 5 and 6 and 6 from oxygen, total 11 electron. Therefore, nitrogen monoxide, if you say nitrogen monoxide neutral, it is actually a free radical. It's actually a free radical having one electron in the anti-bonding orbital. Therefore, it cannot act as a ligand. It cannot act as a ligand. Therefore, it is actually the NO plus. NO plus or the NO minus is actually acting as a ligand. So when to follow NO plus, when to follow NO minus, which we'll be discussing it later. So when coming to the nitrosyl level is 11 electron donor, the nitrosilicon NO plus or NO minus, which is a 10 or 11, 12 electrons, they can readily act as a ligand, especially the nitrosyl, the NO plus can act as two different mode of coordination. First, we talk about the terminal, and we always have a bridging ligand. Look at here, you have a terminal means you have a metal, carbon, nitrogen. You can also have a nitrosyl in the bridging mode, and clearly indicating the nitrosyl is a better pi accepting ligand. So that's for the thing. The another interesting aspect with respect to the terminal mode of bridging, even in the terminal mode of bridging, the nitrosyl can adapt two different mode of coordination. One we talk about the linear, the other one we talk about the bent. So what is meant by linear and bent? If you have the bonding between metal, nitrogen, and oxygen is almost close to 180 degree, then we say it is a linear mode of coordination. If the metal, nitrogen, oxygen, the angle is around 120 to 115, we say it is a bent mode of coordination. Therefore, the nitrosyl can easily act as a linear mode of coordination, bent mode of coordination, as well as in the bridging mode of coordination. We want to know how much electron it is contributing in each and every case. As I said, if you remember correct, the last class only I told, the linear nitrosyl will contribute 3 electrons. The linear nitrosyl will contribute 3 electrons when it is acting as a terminal coordinator linear mode of coordination. The terminal mode of coordination, if it is a bent, it will actually contribute only 1 electron. And in case of bridging, it again will act as a 3 electron donor. So bridging, bent and linear and bridging is a 3 electron donor, whereas in case of the bent mode of coordination, it is a 1 electron donor. This is a simple rule, and this is applicable only if you follow the neutral atom method, not the donor pair method. Donor pair method means a different concept. Actually, we are not following. Therefore, we have to understand the nitrosyl is a 3 electron donor in terms of the terminal linear, 1 electron donor in terms of the terminal bend bottom coordination, and a 1 electron donor in terms of its 3 electron donor in terms of its bridging mode of coordination. Now, if you want to ask me the how this 3 electron, how this one, look at here. This is talking about the neutral atom method, what we are actually following. You can see there are 3 electrons are present in the frontier orbital, one in the sigma orbital and 1 electron in the anti-bonding orbital. These 3 electron actually donated to the metal center to form the metal nitrogen sigma bond. Therefore, the linear nitrosyl is actually a 3 electron donor. Once the single electron present in the pi star orbital also given, there is a empty pi star orbital is arising. Therefore, the nitrosyl is actually have a low energetically lying pi star orbital is there. Therefore, that can be utilized for making the pi accepting ligand. Therefore, the nitrosyl is actually a very good sigma donor as well as a very good pi accepting ligand, and that is how we could be able to explain in terms of the neutral atom method. Neutral atom method, terminal with a linear mode, the bond angle between metal, nitrogen, and oxygen should be close to 165 to 180, mostly close to the 180. Okay, but how the people will explain in terms of the bent mode of coordination in terms of the neutrosyl? In the bent mode, you have an only one electron, the 1 electron present in the anti-bonding orbital alone could be able to donate the electron to the metal orbital, whereas the lone pair of electron is actually not in a position. Look at here, this is lone pair of electron is actually presented here. This lone pair of electron is actually not in a position to donate to the metal center. Therefore, that's only 1 electron which is present in the pi star orbital, which will be the donating to the metal center, and that's the reason we are saying it's actually a 1 electron donor. And look at the bond angle, the metal nitrogen oxygen bond angle is close to 120 to 120, then we can say it is a then we can say it is a bent mode of coordination. That's what we talk about. But actual scientific method, remember, actual scientific method, whatever the method we are following, neutral atom method is only applicable to find the total valence electron. That's the reason I'm saying, if in case of neutral, if in case of the terminal linear mode of coordination, nitrosyl is a 3 electron donor, terminal bent mode of coordination 1 electron donor, and we talk about the bridging nitrosyl is actually 3 electron donor, all belongs to the neutral atom method. Only purpose is to calculate the total valence electron. But if you ask me the correct, if you ask me the correct technical aspect or the current scientific method of explaining the nitrosyl is the, when I say linear nitrosyl, it is better to mention them as NO plus. So linear nitrosyl can be treated as a NO plus, and remember, therefore, if you found linear nitrosyl is actually a linear mode of coordination, then the charge on the ligand is actually positive charge. That's the reason, if I remember, in the first class I said, not only the anionic ligands can, now anionic moiety only can act as a ligand. We have an example of positively charged moiety can also act as a ligand, and this is one such an example where you have a NO plus, where you have an NO plus. This NO plus is actually acting as a ligand, and NO plus means we actually removed a one electron in the pi star orbital. Now you have a pair of electron present in the sigma orbital, which can be donated to the metal center to form a sigma bond, and you have an empty pi star orbital present in the ligand empty pi star orbital, which can be utilized to accept the electron from the metal center. Therefore, your nitrosyl is actually a good sigma donor as well as a pi accepting ligand, and therefore the real scientific method, the donor pair method, where the nitrosyl will actually acting as a 2 electron, it's actually acting as a two, only a 2 electron donor. That is the proper scientific method. And if you want to calculate the oxidation state, if you want to calculate the oxidation state of the metal, then it is, you have to find out whether the linear, whether the nitrosyl is linear or bent. If it is linear, it should be given as a positive charge. Okay, if it is a linear, it should be given as a positive charge. And coming to the bent mode of coordination, there we actually call them as a NO minus. NO minus means we actually added one more electron, and look at here again, and again a 2 electron now actually present in the anti-bonding orbital, and these 2 electron will now be donated to the metal center to form the sigma bond, and the same the empty pi, after the donation there will be a vacancy in the NO, in the pi star orbital, that will be utilized for making the pi back bonding ability. Therefore, this is what the thing. And again, if you talk about the total electron contributed by the NO minus in terms of the real scientific method, the donor pair method, it will contribute 2 electron. Okay, therefore, NO plus, NO minus, no problem. It always acting as a 2 electron donor in terms of the donor pair method. But if you are following the 18 electron rule, if you are following the neutral atom method, then it is a linear 3 electron donor, bent 1 electron donor. Therefore, it is more important. Okay, so that's the reason. If I remember, if I, as I said correctly, any standard book, if you have seen the coordination chemistry, and they are, if they are giving the spectrochemical series, if a book is stating NO as the strong ligand, that is actually wrong, because NO cannot act as a ligand. NO doesn't have the ability to act as a ligand, because NO is a 11 electron donor, but NO plus, the linear nitrosyl or the NO plus is actually the better pi accepting and a very strong sigma donor. Therefore, a very good standard book should always mention the spectrochemical series should end with the NO plus, not the NO. Not the NO. NO, if they are mentioning as an NO, then they are missing something. That is not the correct way of representing the nitrosyl ligand. The correct way of representing the correct way of representing the nitrosyl ligand is actually the NO plus, not the NO, not the simple NO. That is what we have to understand. Therefore, the nitrosyl can adapt to a different mode of coordination in a terminal, linear and bend. If I'm talking about the neutral atom method, is a 3 electron and 1 electron process. If I'm talking about the real scientific method, donor pair method, is a 2 electron contributor in both the linear and bend. But if you want to calculate the charge, if you want to calculate the oxidation of the metal, then you should consider linear nitrosyl as NO plus and bent nitrosyl as a NO minus. And that is what we want to, we need to correct it that way. The NO plus is a linear nitrosin and 3 electron donor and a very strong pi accepting ligand. If you're comparing that one NO minus, it's actually 1 electron donor and they are not that much pi accepting electron. But yeah, this is what we talk about next time. But if the nitrosyl is in the bridging mode, the nitrosyl, whether it is bridging a 2 metal center or a 3 metal or a 4 metal, it's going to donate only 3 electron, and that nitrosyl should be treated as a neutral moiety. Because nitrosyl only when it is in neutral form, the nitrogen monoxide or the nitrogen oxide gas, the nitrosyl, nitrogen monoxide, this is 11 electron species. Only if it is in the bridging mode, it should be considered as a neutral and it is a 3 electron donor, both in terms of I think this is what we have to say the nitrosyl ligand. Is that clear? Punjapa?
Yes, sir.
The difference between linear and bed nitrosyl. Punjapa?
Yes, sir.
Is it clear? Any doubt? Okay, fine. See, now the question comes. See, for nitrosyl, we always use only the same source. Something like nitrogen monoxide is the source we will be using, or the nitric or the nitrous acid HNO2. We always use that as a source. But how the nitrosyl can adapt either the linear mode of coordination or bent mode of coordination? There are some cases in the same metal center, it can adapt both the way. It can adapt a bent mode of coordination, linear mode of coordination. So that is actually decided by the metal and metals oxidation state. If the metals are in lower oxidation state, then the nitrosyl will adapt a linear mode of coordination. Why? If the metals are in lower oxidation state, they have huge amount of electron density, and therefore it can be easily and using the strong pi accepting ligand like nitrosyl can electron transfer density can be transferred to the nitrosyl. Therefore, the metal if the metal is in lower oxidation state or metal have a higher electron density, the linear nitrosyl will the nitrosyl will adapt a linear mode of coordination. Whereas if the metals are in higher oxidation state or it have a very few less electron density, therefore it makes the nitrosyl to adapt a bent mode of coordination. Therefore, because the bent mode of nitrosyl is actually a poor pi accepting ligand, and therefore the metal's electron density decides the thing. For example, look at here. Can anyone tell me what is the oxidation state of the chromium in this complex? In the complex, chromium oxidation state in the what is the oxidation state of chromium?
0, sir.
0. எதுவா 0? எப்படி 0 சொல்றீங்க?
Cp ring -1, fluorine -1,
This is minus
NO,
1, minus 1, and then
NO +1 +1.
yes, right. Because in this case, the nitrosyl is actually a linear mode of coordination. Therefore, you should treat as a +1. Therefore, the oxidation state of the chromium in this case, it is actually actually the 0 oxidation state. And can you please tell me what is the oxidation state of iridium in this compound? The oxidation state of iridium in this compound.
+3, sir.
Exactly, it is +3. Higher the oxidation state, electron density will be less, therefore back bonding will be less. So therefore nitrosyl will be placed in such a way that it won't need more electron density. That's the reason nitrosyl is kept as that as a low electron and as a bent mode of coordination, and that is what we talk about. And these are the examples. I mean, இதுவரை கேட்டதுல சார் example அவ்வளோ the values of the nitrosyl ligand, the bridging, terminal bridging, we talk about the terminal, linear and bent mode of coordination, and we have the bridging coordination. This is here. So ஓரளவுக்கு மெமரைஸ் பண்ணிக்கோங்க. இன்ன வரைக்கும் யாரும் கேட்கல, பட் இதுக்கு மேலேயும் கேட்காம இருக்குன்னு சொல்ல முடியாது. அது we need to move forward. So you have to remember the values for the stretching frequency, linear stretching frequency. You have to adapt it. Okay, so And these are some examples. Look at here. There are classes where you can see both the linear, both the bridging, both only terminal, and you can have a bent, and you have a linear mode of coordination. Therefore, anything is possible. Only depends upon the metal oxidation state and the metal oxidation and the charge. So higher the charge, you'll go for the linear mode of coordination, whereas the higher oxidation state will prefer for the bent mode, the lower oxidation, larger electron state going for the linear mode of coordination can be obtained. And these are the various way we could be able to prefer. But when you're talking about the synthesis, the true homoleptic compound, look at here. In all these cases, we have a nitrosyl ligand, but the nitrosyl ligand is not exclusive. It is actually always a combination with some other ligand, either the carbon monoxide or phosphorus or some other ligand will be present. But look at these examples. This is the only one example, if I remember correct. So far, that's not the only one. The isoleptic chromium nitrosyl compound is known. It's actually a tetrahedral structure. Can you please say what is the oxidation state of chromium in this compound? இந்த இடத்துல குரோமியத்தோட ஆக்சிடேஷன் ஸ்டேட் எவ்வளவுப்பா? The homoleptic nitrosyl compound. Isoleptic nitrosyl or homoleptic nitrosyl. The oxidation state of the chromium compound?
-4, sir.
Exactly. The oxidation state is -4. Remember, already metals are electron rich, and now you have a -4. Therefore, literally meaning there are 4 electrons. There are 4 electrons are actually the higher than what is needed for the chromium atom to be stable. But even though it has a huge amount of electron density, this compound is said to be stable. How it is possible? Even though how it is possible? This is because even though the metals are in lower oxidation state, huge amount of electron density, there are four linear nitrosyl ligands are present, which will take care of the excess electron density. And then now you imagine the power of pi accepting ligand. It could able to take up almost equal to a 4 electron, like meaning the literally meaning 1 electron per 1 ligand. That was a huge. That's what I say. The linear nitrosyl, it is so far the strong pi accepting ligand whatever we have seen up to date. நம்ம என்னதான் எவ்வளவுதான் பேசினாலும் சரி, கார்பன் மோனாக்சைடு இல்ல கார்பன் டெல்லியம், கார்பன் டெலூரியம் இல்ல பாஸ்பரஸ்ல டிஃபரண்ட் சப்ஸ்டிட்யூட் என்ன போட்டாலும் சரி, so far the most pi accepting ligand is nothing but the linear NO plus. The linear NO plus is the most pi accepting ligand so far known in the literature. Okay, now I have another question. If you are provided, I'll give some space. Yeah, if you are provided with like say both PPH3 and nitrosyl, or you have a nitrosyl ligand and carbon monoxide have to be attached in the same metal center, then what could be the geometry exhibited by this true strong pi accepting ligand? Both your carbon monoxide is also strong pi accepting ligand, your nitrosyl is also strong pi accepting ligand, especially the PPSC also the strong pi accepting ligand, nitrosyl also kind of a strong pi accepting ligand. Therefore, how the metal uh, the metal complex is actually formed out of these two strong pi accepting ligand, then can you please tell me what could be the position of these two strong pi accepting ligand? Either these two strong pi accepting ligand has to be kept at the trans position, or they have to kept at the cis position. இந்த ரெண்டு ஸ்ட்ராங் பை அக்செப்டிங்குமே ஒரே மெட்டல் இருக்கணும். இந்த ஒரே மெட்டல் இருந்ததுன்னா அது சிஸ்ஸா இருக்குன்னு ஆசைப்படுமா, டிரான்ஸா இருக்குன்னு ஆசைப்படுமா? What could be your answer? என்ன காரணமா trans? What is the reason for the true pi accepting ligand to occupy the trans position? என்ன காரணம்?
It shows trans effect.
Trans effectனா ஒன்னு புடிச்சு வெளியே தானே தரணும். இப்போ நைட்ரோசிலா கார்பன் மோனாக்சைடு கேட்டீங்கன்னா நைட்ரோசில் will be strong pi accepting ligand, therefore it allows the carbon monoxide go outside. அப்ப எப்படி சிஸ்ல உட்கார முடியும்? அதானே trans effectனா, right? That is called a trans effect. யாராவது வந்தாங்கன்னா which is the strong pi accepting ligand, will direct them the opposite ligand to go out. If linear nitrosyl and carbon monoxides are present, the nitrosyl will ask the carbon monoxide to go out and allow the space to come and occupy for the incoming ligand. அப்போ அந்த காம்பவுண்ட் ஸ்டேபிளா இருக்குமா இருக்காதா? It is undergoing some sort of substitution reaction. Therefore, the ideal thing is that when you have a you have a two strong pi accepting ligands have to be present in the same complex. It is advised them to be placed in the cis position. What is the reason? See, for example, if I am putting the strong pi accepting ligand in the cis position, therefore these ligands would also share the same orbital. If the two ligands are in the same and in the trans position, they have to take up only the one orbital, and through that one orbital only, it has to take up all the pi electron density. Therefore, a lot of problem arises, and then it will create a distability. I mean, it will make the compound unstable. Therefore, they decompose. But when they are put it in the cis position, here carbon monoxide, here NO position, this will actually contact with another orbital. This is actually contact with another orbital. Therefore, the pi accepting competition is minimized. Therefore, each and every ligand like nitrosyl and carbon monoxide will equally accept the pi electron density from the metal center. Therefore, they will not going to disturb the metal center, and they become much stronger. Therefore, if you are given with a choice, and they were always preferred to be in cis position in order to minimize the competition for the pi back bonding from the same orbital. If it is a strict, if it is putting the trans means only one orbital, either not that dxy or dx square minus y square orbital will be there. Therefore, the two ligand actively pulling off the electron density from the same orbital, which make the compound to be destable or unstable. Therefore, it is better to have these two good isotonic ligand in this cis position. Therefore, it is very much easy for the mutual sharing of electron, and that is what exactly happened. If you remember correct, what is Voskos complex? Voskos complex என்ன பார்த்தோம்? What is the name compound? What is the structure of Voskos complex? The molecular formula? Voskos complex structure ba? Iridium,
Iridium,
CO,
PPH3 twice,
Cl,
CO,
PPH3.
Cl.
Yeah, correct. We say it is a trans. Why it is trans? It is trans because, sorry, I think, yeah, it should be here. It should be here, COCl, and this should be PPH3. This is trans COCl PPKs. Your phosphorus are in trans, but look at the geometry of the most pi accepting ligand carbon monoxide and PPKs3. They are cis. They are cis. Why? Only if I'm putting it in the cis position, they will become strong, and that is why the two pi accepting ligand will always occupy the cis position, and that is what reflecting here. And these are some data. You can see the data corresponding to the IR data corresponding to the linear or bent mode of coordination or terminal or bridging mode of coordination with respect to the nitrosyl and carbon monoxide. So if we are discussing the nitrosyl, or if you are saying nitrosyl is the most pi accepting ligand, and then what about its congener? Instead of having NO plus, let's say like NO plus, NS plus, N selenium plus, and N tellurium plus, which will be the most strong pi accepting ligand? Is it NO plus or N tellurium plus? We are actually discussing the parallel chemistry with respect to the carbon monoxide. And when we carbon monoxide, carbon monosulfur, monoselenium, monotellurium, we found that carbon monotellurium ligand is the most pi accepting ligand, and that is a 10 electron species. If you talk about the mono nitrosyl, NO plus, N sulfide, N selenium, N tellurium plus, they also 10 electron, and their hemodiagram are almost same. Then my question is that among these nitrosyl family, which is the most strong pi accepting ligand, the NO plus or N tellurium plus? இது இப்போ strong pi accepting ligand இருக்கும். அப்படி இருந்தா என்ன reason?
Second orbital.
என்னப்பா n?
Second orbital.
அப்ப ஆன்சர் வந்துட்டு
Second orbital.
இல்ல ஆன்சர் எது ஸ்ட்ராங் பை அக்செப்டிங் லிகாண்ட்?
Tellurium.
ஓகே 10 டெலிகம். ஓகே ஹவு மெனி எத்தனை பேர் ஒத்துக்கிறீங்க? நான் கொஞ்சம் இறையுதுப்பா வாய்ஸ். எத்தனை பேர் வந்து ஒத்துக்கிறீங்க n டெலிவரி இஸ் தி பெஸ்ட் பை அக்செப்டிங் லிகாண்ட்? வேற யாராவது ஆன்சர் தோணுதா? How many of you are accepting the n tellurium plus is actually the very good by accepting? எத்தனை பேர் ஒத்துக்கிறீங்க? நீங்க சொல்லுங்கப்பா, ஒத்துக்கிறீங்களா இல்லையா? இல்ல வேற ஏதாவது ஆன்சர் இருக்கா உங்களுக்கு? ஹலோ, கேக்குதாப்பா? நான் கேட்குற கேள்வி புரியுதாப்பா உங்களுக்கு? Am I audible or not? Is there any network issue? சொல்லுங்கப்பா. உங்களோட வாய்ஸ் ரொம்ப நாய்ஸியா இருக்குப்பா. ஐ திங்க் மேபி ஹெட்ஃபோன் இஷ்யூ நினைக்கிறேன். மற்றவங்களுக்கு கேக்குதாப்பா?
Yes, sir. Yes, sir.
இப்போ n tellurium பெஸ்ட் பை எக்ஸாம்பிள் ஒத்துக்கிறீங்க எல்லாருமே? Are you accepting n tellurium is the most by accepting ஒத்துக்கிறீங்களா இல்லையா? Say yes or no. What is the problem? நானும் மார்க்லாம் கொடுக்க போதில்லை. We are coming here to learning. We need to discuss. அப்பதான் உங்களுக்கு புரியும்.
No,
Are
sir.
you accepting? Why? ஏன் ஒத்துக்க மாட்டேங்கிறீங்க? What is the reason? In case of carbon monoxide, carbon sulfur, carbon selenium, tellurium, the carbon tellurium is the most by accepting ligand. அதே இங்க ஒத்துக்க மாட்டேங்கிறீங்க. ஏதாவது சொல்லுங்கப்பா. தூக்கு மாதிரி தானே எல்லாத்துக்கும். ஹலோ,
இல்ல சார்.
ஃபர்ஸ்ட் ஆஃப் ஆல் ரெண்டு டவுட். வாய்ஸ் நல்லா கேக்குதா? நான் கேட்குற கேள்வி உங்களுக்கு புரியுதா? நான் பேசுறது உங்களுக்கு புரியுதா?
எஸ் சார்.
Yes, sir.
பவர் பாயிண்ட் தெளிவா தெரியுதா?
ஆமா சார் தெரியுது.
ஓகேப்பா ஃபைன். அப்ப ஏதாவது ஆன்சர் சொல்லுங்க. ஓகே, ஐ வில் கோ வித் ஆன்சர். தெரியலன்னு சொல்லுங்க. நோ ஐடியா சார், நோ கமெண்ட், எனக்கு புரியலன்னு சொன்னா ஓகே ஃபைன். ஓகே, கேரக்டர்
By accepting character decreases, sir.
எப்படி டிக்ரீஸ் ஆகுது? ஏன் டிக்ரீஸ் ஆகுது? why it decreases?
Electronegativity.
Okay, I think he already studied somewhere. Okay, fine. That's what. See, correct. What he said is correct. Now, if you compare the pi accepting or pi accepting nature of NO plus with N sulfide, N selenium, actually the nitrogen monoxide is still dominating. This is actually reverse to that of your carbon monoxide, carbon monosulfide, where the carbon tellurium was found to the most pi accepting ligand, whereas in case of the nitrosyl, thionitrosyl, selenitrosyl, the nitrosyl, the linear NO plus is the most strong pi accepting ligand, whereas your N sulfur, N selenium, N tellurium is not a very good pi accepting ligand. Therefore, if you ask me to write the overall the spectrochemical study, the strong pi accepting the strong ligand is only the NO plus, but among the carbon monoxide is actually carbon tellurium. That's a huge difference. Why? அந்த இடத்துல நம்ம வந்து கார்பன் சல்ஃபர்ல பிகாஸ் வி ஹாவ் எம்டி டி ஆர்பிட்டால் சேம் எனர்ஜியா இருக்கும். அப்ப ஈஸியா பாயக்ஸ்மன் பேசுற நம்மால ஏன் இந்த இடத்துலயும் அதே தானே சேம் திங், வி ஹாவ் செலனியம், வி ஹாவ் சல்ஃபர், both will have a empty d orbital, therefore they also have a symmetry to that of metal, therefore the pi electron density has to be transferred. This is what we expected, and we expected n tellurium plus should be acting the most pi accepting ligand, but that is not true. Therefore, besides the empty pi star orbital, besides the energy, besides the same, we also in need of one more parameter, something called polarity. Something called polarity. When all these are matches, the polarity, the empty pi star orbital, all these are matches, then only we can say the ligand is a better pi accepting ligand. What actually the problem with the N sulfur, N selenium is there? If we talk about the nitrogen monosulfide, the electronegativity difference between the nitrogen and sulfur is very much huge difference is there. Therefore, the molecules are more polar in nature, and that's the reason they are not able to accept it. Whereas when you talk about the other ligands like a carbon monoxide, carbon monosulfide, the carbon, yes, they almost have a same electronegativity. Therefore, the polarity is less. And if you talk about in the next one, we are talking about something called a nitrogen, where the polarity is zero. The homonuclear diatomic molecule, the polarity is zero. Therefore, what is actually the minimum requirement for a ligand to be act as a pi accepting ligand is that they should have a empty pi star orbital. They should have some polarity. The bond should have some polarity, but the polarity should not be greater. Should not be greater or should not be very low, close to zero. It should have an average value. You should have an average value. Then only the ligand can accept the pi electron density from the metal center. Therefore, what we understand from the nitrogen monosulfur, nitrogen monotellurium, nitrogen monoselenium, all are the electronegativity difference, but the nitrogen and sulfur or selenium or tellurium is more. Therefore, the nitrogen monosulfide, nitrogen monoselenium, nitrogen monotellurium, all are not a very good pi accepting ligand, and that's what we want to conclude. But that is not true with your carbon monosulfide or monotellurium, monoselenium. They almost have the same electronegativity, almost same, not exactly equal. Therefore, they could able to act as a very good pi accepting ligand. And then in the same series, we also have a dinitrogen N2. N2, the total valence electron is 10, similar to that of carbon monoxide. Therefore, 2 electron will be present in the lone pair of electron present in the sigma orbital, which can be donated to the metal center to form a sigma bond, and you have a empty pi star orbital is present. Therefore, we can say the nitrogen is a pi accepting ligand. So the Moore diagram is ditto, is almost identical to that of your carbon monoxide, but the electronegative difference between the dinitrogen is zero. Therefore, the electron difference is zero. Therefore, this N2, even though they have an empty pi star orbital, it is not capable of accepting the pi back bonding. Therefore, dinitrogen is a very strong sigma donor, but a very poor pi accepting. And this is because the polarity difference is nil. ரொம்ப அந்த டெல்டா நெகட்டிவ் டிஃபரன்ஸ் எலக்ட்ரானிக் டிஃபரன்ஸ் ரொம்ப அதிகமாகவும் இருக்கக்கூடாது, ரொம்ப கம்மியா ஜீரோ இருக்கக்கூடாது. இட் ஷுட் ஹேவ் அ மாடரேட் வேல்யூ லைக் நைட்ரோசில் ஆர் CO. Then only the ligand is said to be a very good pi accepting ligand, which is actually with respect to the dinitrogen, the polarity difference is zero. Therefore, they cannot act as a very strong pi accepting ligand. But still, nitrogen is a pi accepting ligand. There is no doubt in, but they are not strong as that of the cyanide or carbon monoxide. And that is what we talk about the bonding nature. And again, you can see it can form the terminal or can form a doubly bridging. All this can be accepted. That is what we talk about. That's all about the dinitrogen compound. You can also make a lot of nitrogen compound. Is that clear? Dinitrogen, nitrosyl ligand. அதெல்லாம் புரிஞ்சுதாப்பா அதை பத்தி எப்படி அந்த ஸ்ட்ரக்சர் பாண்டிங் எல்லாம்?
Yes, sir.
sir.
Okay. So, and we move to the hydride ligand, the H minus. So H minus mean hydrogen means one electron. H minus mean one more electron. Therefore, H minus is a very simple ligand. It's a very simple ligand, and H minus is actually a single atom ligand. It's not a single atom ligand. There is no other. Therefore, in case of H minus, we have only one sigma orbital that is now filled. No, not even anti-sigma bond. No anti-sigma. No anti-bonding orbitals are available. Therefore, hydrogen or the hydride ligand is a strong sigma donor ligand, but it doesn't have any pi accepting nature. Doesn't have any pi accepting nature, and still it is actually called as the pi accepting ligand, and that's how it is because its physical property, the metal hydride physical property, are almost same. They are mostly like an organic compound. Only on that basis only we could be able to understand the hydride, the metal hydride is actually an organometallic ligand, not on the basis. And this H minus can act as can be of terminal, can be of double bridging, can be a triple, or can also bridge 7 or 8 7 or 8 metal center, but whatever it may be, the hydride ligand actually have only one electron. Therefore, it is actually a one electron donor. It's about the neutral atom method. If you talk about the donor pair method, it's a 2 electron. Therefore, it's only the 2 electron donor, and that is what, even it can bridge any metal, no problem. Any number of metal, it will going to occupy only the 1 electron as per the neutral atom method. Okay, now we move to the another ligand called dihydrogen H2. So H2 means two hydrogen atomic hydrogen combined together to form a H2 molecule. Therefore, the MO diagram will have a sigma and anti bonding orbital. So therefore, you can see a pair of electron present in the one sigma orbital, which can be donated to the metal center to form a sigma bond, and you can see an empty pi star orbital is present. Therefore, sorry, not the empty pi star, not the sigma star orbital, empty sigma star orbital, which can be utilized for making a pi accepting ligand, pi accepting electron, pi accepting orbital can be utilized. And remember, this is only one problem here. The pi back bonding actually going to the sigma star orbital. In previous cases, mostly the sigma star orbital, and you know that the overlap of sigma bond is much more stronger. Therefore, anti-bonding will also be more stronger or higher in energy, whereas a pi star is actually not that much energy. The overlap is poor, therefore the energy will be less, therefore literally low in energy. Now the question is that if the metal has the tendency to back donate the electron, what could be the status? What could be the status of the metal dihydrogen? Whether they will be stable or they will be decomposed to metal hydride. Now we are putting the electron in the anti-bonding orbital. அப்ப என்ன ஆகும்?
Unstable, sir.
Which is unstable. What happened? What happened to the complex?
Decompose.
Decompose.
No, it won't decompose. Rather, what will happen? The dihydrogen break into a dihydride, and therefore will form the metal dihydride. So dihydrogen MH2 will let as the pack bonding goes and goes and goes, more and more electron density going to the sigma star orbital. It makes the hydrogen bond weaker and weaker and weaker. What one particular time the hydrogen bond cleave. Look at here, the bond is now cleaved here. Therefore, the metal became dihydride. So what is the meaning? If we have a metal attached with the H2, then we say it is a metal dihydrogen. When we have a metal it attached with the with the bracket twice, it is actually dihydride. Therefore, in this case, this is like a metal and you have a hydrogen and you have a hydrogen. How does it happen? Because of the pi back bonding, and we have studied the bond order will be zero. Bond order will be reduced if I'm adding the electron in the anti-bonding orbital. Now I'm adding the anti-bonding orbital of the electron. Therefore, the bond order of hydrogen became zero. Therefore, they cleave and added as a simple hydride to the middle center, and that we talk about the hydride. So this is what the interesting aspect with respect to the dihydrogen ligand. Therefore, too much of pi back bonding from metal to the ligand will cleave the hydrogen into dihydride and connect to the metal center. Therefore, how to prevent this one? We have to make sure that the metals are in larger oxidation state. Metals are in, if you see, for some sort of application, we need to have the complex. The complex should have a dihydrogen, H2 should be present in that molecule. In that case, if I want to retain H2 as H2, I need to make sure that my metal complex is in really higher oxidation state. If it is really higher oxidation state, therefore the pi back bonding becomes poor, therefore H2 molecule remain intact. On the other hand, I can also substitute the other ligand with the very good pi accepting ligand. Therefore, the metal's excess electron density will go to the other part of the molecule, leaving the double bond remains the same, and that's how we could be able to prevent the and the prevent the hydrogen cleavage when you have a dihydrogen ligand to a dihydrate complex. Is that clear? சொன்னது புரிஞ்சுதாப்பா? ஏதாவது புரியாம இருக்காப்பா? Is that fine?
Yes, sir.
Okay, so we'll move to the next one. Next one is another interesting set of ligand. We have something called a phosphorus. We have something called a phosphorus. What is the phosphorus? Before going to the phosphorus, we have seen this is that the title says spectator ligand. What do you understand from spectator ligand? Any idea? Spectatorless. Sorry. Spectator ligand. What do you understand by the term spectator ligand? Never சொல்லுங்க spectator ligand na?
Not involved in the reaction.
Correct. See, remember in this case, in previous case, what we discussed with the metal dihydrogen, due to some reason, the pi back bonding, the hydrogen bond will cleave and to form the dihydrogen. Therefore, we actually start with the H2 molecule, but end up in getting H minus. And previous case, when we have a something, we're discussing reaction mechanism. You have a when we have a something like a metal carbon monoxide, when it's attached with the methyl group, they will be easily converted into the C double bond OCS. This carbon monoxide and methyl combine together to form a acetate group. So whatever the ligand we studied so far, similarly N double bond N nitrogen, it will be reduced to N double bond by this is called diazole. It can be reduced to N single bond N hydrogen kind of a ligand. The chemical form, the name also vary depending upon the metal and other thing. But so that it is indirectly meaning that these ligands are undergoing some sort of chemical reaction, and those we talk about the previous section. But in this case, the spectator ligand, they will not undergo any sort of chemical reaction, but their presence will activate the metal center to perform better, and that is called a spectator ligand. This is called the spectator ligand. ஸோ இது பொதுவாக ரொம்ப சிம்பிளாக சொன்னால், நம்ம ஒரு காலேஜ்லேயோ எங்கேயோ நம்ம மேட்ச் பார்க்க போகிறோம், நம்ம ஒரு ஆடியன்ஸ், வி நெவர் பிளே, நம்ம போய் இறங்கி விளாட மாட்டோம் இல்லையா, வி ஆர் த ஜஸ்ட் அ சிம்பிள் ஆடியன்ஸ், வில் சிட் இன் தி கேலரி அண்ட் என்ஜாய் த கேம். நம்ம அவ்வளோதான் பண்ண முடியும். நம்மளுக்கு பிடிச்சமான டீமு தோக்க போகுதுன்னா கூட நம்ம இறங்கி விளாட முடியாது. பட் நம்ம பிடிச்சமான டீம் தோக்க போகுது, நம்ம எப்படியா ஜெயிக்க வேணும்னா நம்ம அவங்களுக்கு கத்தி நம்ம என்ன பண்ணுவோம், encourage பண்ணுவோம். Exactly the same way your spectator ligand are just like that one. They will not involve, they never involve in any chemical reaction, but their presence actually enhance the rate of the reaction. அதை நம்ம கரெக்டாக டியூன் பண்ணோம் அப்படின்னா it will enhance the reaction, and that is what the two example, the phosphine and N heterocyclic carbene ligand. These are the two example for which we can collectively call a kind of a spectator ligand. First we take the phosphorus ligand. Phosphorus belongs to nitrogen family, whose normal valence is 3 and have a lone pair of electron. Therefore, without doing any charge itself, can act as a ligand through the lone pair of electron. Therefore, the neutral is actually a 2 electron donor. The advantage of this ligand when compared to the other ligand is that, look at here, you have a 3R group, R1, R2, and R3. This R1, R2, R3 can be of same molecule, can be of different molecule, anything. You put any electron withdrawing group, any electron releasing, any electron or electron group, that will bind with, that will alter the property. Remember, in case of carbon monoxide, in case of nitrogen, dihydrogen, we cannot change any of its property. Dihydrogen இப்படினா அப்படிதான், carbon monoxide இப்படினா அப்படிதான், we cannot change anything. But that is not true with your phosphorus ligand. Your phosphorus ligand can be easily tuned. How we can tune it? We can substitute the R group with the electron releasing group, electron withdrawing group. Sometimes we can substitute with the sterically hindered group. All this going to affect the property of the phosphorus, which in turn going to affect the property of the metal center, and therefore which in turn going to affect the catalytic activity. That is what the advantage. Therefore, this is the advantage of having a phosphorus based ligand. So look at here. Say by varying, it can be the change in the steric index can be changed. The basicity or the nucleophilicity can be changed. Donor acceptor can be changed. And look at here, even it can lose one or two ligand and can add more and more a negative charge to the system. Therefore, your phosphine, triphenyl phosphine, a triaryl phosphine will act as a ligand. It's a two electron, it's a neutral one. If you are replacing one of the R group, therefore it is an anionic ligand. Therefore, it can also act as a bridging ligand. It can doubly terminating or a triply terminating. All this sort of things can be easily obtained, and we can have the tendency also will vary: monodentate, bidentate, tridentate, hexadentate, heptadentate, like this can also be achieved. And yeah, now the thing is that, see, for example, if you have a phosphorus and you have a lone pair of attached electron, this has to be 20 elemental center. But remember, when R equal to F, when your R equal to F, the fluorine, what is the nature of fluorine? The fluorine is the most back electron withdrawing group. Therefore, what will happen? These electron takes up this pair of electron, and therefore the lone pair of electron present in the phosphorus is not readily available coordination. Therefore, when you have a phosphorus substituted with the electron withdrawing group, they are said to be poor sigma donor ligand. But at the same time, it is under forceful condition we make the phosphorus to bind with the metal center. Therefore, the metal will be in huge amount of electron density. The metal look for an alternative way to dissipate the excess electron density. Then what will happen? This is looking at the fluorine, therefore it will send back the electron to the phosphorus, which in turn send back to the fluorine atom. Therefore, this AM ligand will be a very good pi accepting because of the presence of the fluorine atom. Therefore, look at we altered the nature of the phosphorus ligand. It can be act as a very poor sigma donor, but a very good pi accepting. Not the case, because when you have other things, look at here, you have a P methyl group, and you have a pair of electron, and this methyl is an electron releasing group. Therefore, already have a metal electron release, therefore additional two electron. Therefore, nothing to happen. A metal can easily coordinate to the metal center, no problem. But once after the coordination, what will happen? The metal of an electron density, they want to give it back. Where to give? How to give? Because phosphorus attached with electron releasing group, they are not in need of any electron any so what I can say, they are not in need of any back donation, because already methyl group is electron releasing group, and therefore what will happen? The same ligand will act as a poor sigma donation ligand. At the same time, yeah, a very good sigma donor ligand, but a very poor pi accepting ligand, and that is what we could be able to tune it. That is the more advantage of the phosphorus based ligand. Look at here, you can see when you have PCY trace, they are very good pi accepting ligand. When you say PCL3, PO3, another thing, it is actually the very poor sigma donor, and a very good pi accepting ligand can be achieved. Therefore, depending upon the requirement, we can tune the nature of the phosphorus, whether they can act as a strong sigma donor or poor acceptor. We could be able to tune, which is not feasible with the other system. That's the interesting aspect with respect phosphorus case. Now, we want to know how the bonding is actually making. So simply saying how the bonding, how we have phosphine ligand is actually interacting with the metal. எதுப்பா sigma donor, எதுப்பா pi accepting ligand? Phosphorus இந்த மாதிரி இருக்கு. இந்த மாதிரி ஒரு பாஸ்பரஸ் இருக்கு. இந்த பாஸ்பரஸ் வந்துட்டு எப்படி பாண்டிங் இன்வால்வ் ஆகும்? வாட் இஸ் தி which is sigma orbital, which is the pi accepting orbital? சொல்லுங்கப்பா. இந்த மாதிரி ஒரு பாஸ்பரஸ் எலக்ட்ரான் ரிச் பாஸ்பரஸ் வச்சுக்கோங்களேன். இது எது சிக்மா பாண்டிங் ஆர்பிட்டால்?
லோன் பேர் வந்து சிக்மா பாண்டிங்.
லோன் பேர் வந்து சிக்மா. பை அக்செப்டிங் ஆர்பிட்டால்
ஆர் குரூப் ப்ளஸ்
ஆர் குரூப்பா? வேற ஏதாவது ஆன்சர்ப்பா? வேற இருக்காது. என்ன எதிர்பார்க்குறாங்க ஃபர்ஸ்ட் ஆஃப் ஆல்? ரிப்ளை பண்ணுங்கப்பா, அப்பதான் நல்லா இருக்கும். இல்லாட்டி போரிங்கா இருக்கும். ஒரே சைடே பேசணும், போர் அடிக்கும். வாட் இஸ் யுவர் எக்ஸ்பெக்டேஷன்? எது பை அக்செப்டிங் நேச்சரா இருக்க முடியும்? எம்டி பை ஸ்டாரா இல்ல வேற எதுமா?
5 ஸ்டார் ஆர்பிட்டால்.
பை ஸ்டார் ஆஃப் வாட்?
ஐ திங்க்
லைக் பாஸ்பரஸோட பை ஸ்டார். பாஸ்பரஸோட பை ஸ்டார். ஓகே, வேற ஏதாவது ஆன்சர்ப்பா? லைக் அமோனியா மாதிரி. பட் ஆக்சுவலா அது இட்ஸ் நாட் ராங். நீங்க யாரும் சொல்ல மாட்டேங்கிறீங்க. இட்ஸ் ஆக்சுவலி ராங் ஆன்சர். I was expecting an answer that phosphorus is having a empty d orbital. Therefore, the empty d orbital can be can be with the same energy compared to that of the metal. Therefore, they can act as a pi accepting orbital இருக்குன்னு நான் எதிர்பார்த்தேன். இல்ல கரெக்டா தப்பா? நீங்க யாரும் எதிர்பார்த்தீங்கன்னா இல்ல சும்மா சொல்ல மாட்டேங்கிறீங்களா? யோசிக்கவே இல்லையா? ஒரு பாஸ்பரஸ் லிகான்ல எதுப்பா பை அக்செப்டிங் லிகான்? இதான் சொல்லுங்கப்பா, அப்பதானே பேச முடியும், நல்லா இருக்கும். எம்டி டி ஆர்பிட்டாலா இல்ல பை ஸ்டார் ஆர்பிட்டாலா இல்ல வேற எதுவுமா? ஐ மீன் ஆடிபிள். சொல்லுங்க.
சார் பை வராது சார், ஏன்னா டபுள் பாண்ட்ஸ் இல்லைங்களா சார்.
அப்ப இதுல எங்க வருது? இதுல கார்பன் ஆக்சைடு இருக்கா? ஓகே, அப்ப என்னதான் இருக்க முடியும்? அப்ப டி ஆர்பிட்டாலா? எம்டி டி ஆர்பிட்டால்?
இல்லை சார், அது மாலிகுல் ஆயிடுச்சுல சார். அப்போ மாலிகுலர் ஆர்பிட்டாலாம் சார் ஆன்டை பாண்டிங் ஏதாவது.
அதான்ப்பா மாலிகுலர். இப்ப எம்டி டி ஆர்பிட்டால அது வந்து பாண்டிங் இன்வால்வ் ஆகல. அப்ப அது நான் பாண்டிங் ஆர்பிட்டால் இருக்கு இல்லையா? தட் நான் பாண்டிங் ஆர்பிட்டால் கேன் பி ஆக்ட் அஸ் எ பை அக்செப்டிங் லிகாண்ட் தானே?
எஸ் சார்.
அதான் ஆன்சர் கேட்குறேன். பாஸ்பரஸ்ல டி ஆர்பிட்டால் இருக்கா இல்லையா?
இருக்கு சார்.
மெட்டல்ல டி ஆர்பிட்டால் இருக்கா இல்லையா?
இருக்கு சார்.
இன்ஃபேக்ட் சொல்ல போனா ரெண்டுமே ஒரே. நான் 3D மெட்டல் சொன்னா ரெண்டுமே 3D தான். பாஸ்பரஸும் 3D இருக்கு, உங்களோட மெட்டலையும் 3D இருக்கு. இப்ப பை பேக் பாண்டிங் டி ஆர்பிட்டால் போகுமா போகாதா? என்ன எதிர்பார்க்குறீங்க? என்ன இருந்தது? ஓகே, ஸோ ஆக்சுவலாக அப்படிதான் எல்லாரும் நம்பிட்டு இருந்தாங்க. அதான் உண்மை. எவ்ரிபடி வாஸ் பிலீவிங், even the cotton, even if you take the book of F.A. Cotton and read the pi accepting nature, everybody was believing that the phosphorus actually have a empty d orbital, therefore no problem in them in acting as a very good pi accepting ligand. But that is actually not true. After we developed so many important valid point in the molecular orbital diagram and we have a very good computing system, the computers with the super fast computer and the calculation software, what we found, the d orbital of the phosphorus is actually not involving in the pi back bonding orbital. Therefore, how to view this one? You can see, you can see a pair of electron present in the sigma orbital, the phosphorus atom, that can be donated to the middle center to form a sigma orbital. To form a sigma orbital. And look at here, if you take the energy level diagram, your 3D orbital present in the phosphorus is actually higher energy, than that of your sigma star orbital. Therefore, the pi accepting orbital is not the pi star orbital. It is actually the sigma star, the PR sigma star orbital. இது 2014 ஒரு சிஎஸ்ஆர் கொஸ்டினாவே கேட்டாங்க. வாட் இஸ் தி சிக்மா, வாட் இஸ் தி சிக்மா பாண்ட், வாட் இஸ் தி பை பேக் பாண்டிங்னு 2014 ஒரு கேள்வி கேட்டாச்சு. But actually, on the question and answer பண்ணும்போது initially my thought was only the 3D orbital of the phosphorus atom, but that is actually not true.
சார்
Even in a
சிக்மா
Wikipedia.
பை டி
சொல்லுங்கப்பா,
பை ஸ்ட்ராங்கா இருக்குமா சார்?
புரியலப்பா.
சிக்மா பை டி பை ஆர்பிட்டல் ஸ்ட்ராங்கா இருக்குமா?
அதுதான் the pi back bonding overlapping. Look at the symmetry. Look at your d orbital symmetry and the p of sigma star orbital symmetry. They are almost same. Sorry, the orbital structure.
பி பை பி பை ஆர்பிட்டல்னா லைக் எனர்ஜி லைக்
No.
ஸ்டேபிளா இருக்கும்.
See, d நீங்க சொல்ற p pi dip orbital வந்து பாஸ்பசீன்ல இருக்கு. p that is also not stable. Actual stable வந்து p ஆர்பிட்டாலும் p ஆர்பிட்டாலும் ஓவர்லாப் ஆகி ஃபார்ம் ஆகிற பை ஆர்பிட்டல் தான் மோர் ஸ்டேபிள். p pi d pi வந்து அந்த அளவுக்கு ஸ்டேபிள் கிடையாது. that is what about the phosphosine. But இந்த இடத்துல it is actually the pr sigma and pr sigma star orbital. Why it is making the bonding? Because their symmetries are same. Look at the symmetry, they are same. And if you ask me the question, why the d orbital, which is actually have a same symmetry, why it is not holding? Because of the high energy. Look at the MO diagram. Where is the pi star orbital? It is too far away. Correct? Papa? Hello? புரியல. ஐ திங்க் புரியல நினைக்கிறேன் நான் சொல்றது.
5 ஸ்டார் கீழ தானே சார் வரும்?
எங்கப்பா 5 ஸ்டார் கீழ இருக்கு? நீங்க தான் நான் தான் எம்போட உங்களுக்கு காமிக்க தான் செய்றேன். லுக் அட் தி டி ஆர்பிட்டல் எங்க இருக்கு? டி ஆர்பிட்டலோட எனர்ஜி இங்க இருக்கு. இது சிக்மா ஸ்டார் ஆர்பிட்டல். அப்ப எது ஓவர்ல பார்க்க முடியும்? எனர்ஜி லோவா எனர்ஜி ஹையா?
லோ எனர்ஜி.
So therefore the anti-bonding orbital, see the pi accepting orbital should be the pr sigma star. இல்ல? இப்ப யோசித்து பாருங்களேன். the other hand, so look at the spectrochemic. இந்த நம்ம சீரிஸ் பார்க்கிறோம். இங்க சைக்ளோஹெக்சைலா இருந்துச்சுன்னா குட் சிக்மா டோனார். பட் அதே இது இங்க வந்து pf3 இருந்துச்சுன்னா சிக்மா புவர் சிக்மா டோனார் சொல்றோம். அண்ட் pf3 இருந்துச்சுன்னா வெரி குட் பை எக்ஸப்டார்னு சொல்றோம். pCO3 இருந்தா புவர் பை எக்ஸப்ட்னு சொல்றோம். If you are saying your d orbital of phosphorus is the pi accepting nature, therefore there is no change in the energy. அப்போ நான் சைக்ளோஹெக்சைல் போட்டா என்ன, ஃப்ளூரின் போட்டா என்ன, புரோமின் போட்டா என்ன, எல்லாமே ஒரே மாதிரி பை அக்செப்டிங் தான் இருந்திருக்கணும். பட் வாட் வி ஃபவுண்ட் இஸ் டோட்டலி டிஃப்ரெண்ட். நான் எலக்ட்ரான் வித்ட்ராயிங் குரூப் போட்டேன்னா they are said to be strong sigma poor sigma and pi acceptor இருக்கு. நான் எலக்ட்ரான் ரிலீசிங் குரூப் போட்டேன்னா they are poor good sigma and poor pi acceptor வருது. அப்ப it is all evidences to the leading that it is not the d orbital present in the phosphorus is not involving in the pi back bonding. It is the pr sigma star. The pr sigma star. And why there is a difference? Look at here. If you compare the energy levels of your pr sigma star when with a different group like fluorine, oxygen, nitrogen, oxygen, the phosphorus having fluorine, nitrogen, the sigma star orbital high energy, therefore pi back bonding to high energy orbital is less. Therefore the phosphorus with the carbon is a poor pi accepting nature. Whereas with the fluorine, the electron withdrawing group on the substituent, it is actually the energy levels are much lower. Therefore it can readily accept the pi back bonding from the metal, and that is how we could be able to explain it. Is that clear now? இப்ப புரிஞ்சுதா?
Yes, sir.
Yes, sir.
So therefore remember, it is not the empty d orbital, it is not the pi star orbital, it is the pr sigma star orbital actually involving the bonding. So now the problem comes here, and one more para. Yeah, this is what we talk about steric intense. We talk about something called Tolman cone angle. So in this case, if I'm substituting, I could able to substitute all the three with the hydrogen atom. all the three with something else. Therefore, I could able to alter the cone angle, or we talk about the cone angle is a measure of the bulkiness as a whole. As the cone angle increases, the bulkiness of the ligand increases, and therefore look at here the triphenyl phosphine PH3, the smallest angle, which is actually a cone angle of 87 degree, and then for the bulky one it is actually it is actually have a 228 the picometer and 118 depending on the bond angle varies, and that's what we talk. Therefore, I could able to tune the ligand not only in terms of this electronic and other property. I can also tune from the steric factor also. I could able to tune it. This is what more important. Okay. Now becomes is the big problem. What will happen to the stretching frequency when you have the phosphorus ligand? As I said, the phosphorus ligands can easily vary that can act as a strong sigma bond or a strong pi accepting ligand. Therefore, if they present together, what will happen? That actually depends upon the R group. If R is an electron releasing group, then phosphorus is actually a very strong sigma donor, but a poor pi acceptor. Therefore, the more pi back bonding will not come to the fourth ligand, and the other silver monoxide ligand will take up the electron density. Therefore, therefore the stretching frequency will be higher. Okay. On the other hand, if you have a no, sorry, it's not higher. It's actually lowest because the phosphorus now acting as a poor pi accepting. Therefore, the pi back bonding will go to the carbon. Therefore, metal carbon bond strong, carbon action become weak, and therefore the stretching frequency will be lower. On the other hand, if I have a fluorine for the same compound with the fluorine actually electron withdrawing group. Therefore, they can act as a poor sigma donor, but a very good pi accepting ligand because of the fluorine atom, and therefore, pi back bonding towards phosphorus will be more, making metal phosphorus strong, metal carbon bond weak, carbon oxygen bond strong, and therefore the stretching frequency will be increased. In case of the carbon monoxide, frequency will be increased. And that is what we talk about. So same thing is explained here. And look at here. When you have a L, the tube-butyl is electron releasing group, strong sigma donor, poor pi acceptor. Look at the as a poor pi acceptor. Therefore, the stretching frequency is slowly keep on increasing. On the other hand, your PF3 is a strong is a poor sigma donor, but a strong pi accepting ligand, and therefore the stretching frequency will be from top to bottom is actually decreasing. This is what we talk about the stretching frequency. Is that clear? உங்களுக்கு புரிஞ்சுதாப்பா?
Yes,
Yes,
sir.
sir.
ஃபாலோ பண்ண முடியுதா உங்களால? ஓகேப்பா, ஃபைன். Yeah. These are the example. Maybe you can work it out a little later. The other type of spectator ligand is the N-heterocyclic carbene. So we will be studying 3 or 4 different type of carbene. Therefore, it is our responsibility to understand it clear. Now I'm saying N-heterocyclic carbene or simply NHC. N-heterocyclic carbon and NHC. So this is a heterocycle, nitrogen containing heterocycle. Look at here, you have a nitrogen containing heterocycle, which will be later converted to the carbene form, which can be attached with the what I can say, the metal center. This is what we talk about. It's a neutral ligand and 2 electron donor, and look at here, you have a R group. You have a R group present on the nitrogen. That R group can be electron withdrawing, can be electron release. I can also put the steric hindrance. Therefore, it is very much easier to compare the spectral data of IR or the bonding, accepting, and ability can be easily obtained, and therefore this is very much. Any problem? Therefore, it is very much similar to that of your phosphorus. I can able to make the carbene ligand as a strong sigma donor as well as a poor as well as a strong pi accepting ligand எல்லாம் மாற்ற முடியும் depending upon the R group. When the R group is in electron releasing group, the ligand is a good sigma donor and poor pi acceptor. When the R is a R is a electron withdrawing group, then it is a poor sigma donor and a better pi accepting ligand is obtained. Okay, this is what we talk about. When it comes to the bonding, as a carbene ligand, in the carbon you have a lone pair of electron which will be donated to the metal center to form a sigma bond, and you can see one of the orbital, either the px or py orbital. Either the px and py orbital is actually involving in the bonding, and therefore it could be able to get the structure done. This is what we talk about, the bonding and sigma bonding, and these are all the examples. And the same kind of argument with respect when you have talking about the phosphorus and carbon dioxide, the same thing can also be done with your carbene-based ligand. Also, the carbene ligand can act as a strong sigma donating ligand, and also a very good pi accepting ligand. Depending upon the substituents, you could be able to do that. Therefore, that's all about the N-heterocyclic carbene. Is there any doubt with respect to the phosphorus and N-heterocyclic carbene? டவுட் இருக்காப்பா? புரியுதா இல்லையாப்பா? ரொம்ப டல்லா இருக்கீங்க இன்னைக்கு. Could you able to follow?
Yes, sir.
Okay. Okay. This is not that much more. I'll skip it. Yeah. Now we are in talking about where still actually, if you remember correct, we have actually classified the ligand into 3 different categories: sigma donor, pi donor, and the benzenite system. Okay, and still we actually focusing on the sigma donor ligand. So therefore, now we talk about in the sigma donor we have a metal carbon double bond. We have a metal carbon double bond. It is almost equal to that of a carbon carbon double bond. Therefore, what type of ligand it will form this kind of metal carbon double bond? It is actually the carbene. What is carbene? Carbene is nothing but a CH2 moiety, highly reactive masses, where you have a 2 unpaired electrons are present, and depending upon the orientation of the ligand and other thing, we classify the carbene into 2 different categories: a singular carbene and a triplet carbene. Singular carbene means you have only one unpaired electron present in the pz or px orbital, whereas the pair of electron present here, we talk about the carbene, the single carbene, and triplet carbene. One electron will be present in each of the orbital, px and the py orbital. And that is called as the triplet carbene. We have a single carbene and you have a triplet carbene. Okay, so with this singular carbene and triplet carbene reacts differently with the metal center to produce the required graphene complexes. Where you can see, when I'm taking the singular carbene and allow them to react with the metal center, it actually produces the Fischer carbene and Petit carbene. It's the name of the compound. Okay, say the Petit carbene and the Fischer carbene. But if I'm using triplet carbene, exclusively give only the straw carbene. So how to differentiate the Petit carbene, Fischer carbene, and straw carbene? The Petit carbene cannot be distinguished. We need to find some alternative technique to find the distinguish. But iron and the so not the iron, the Fischer carbene and the Fischer carbene and straw carbene can be easily distinguished depending upon the substituents on the carbon atom. The substituents on the carbon atom, if the substituents contains the substituted carbon atom, look at this position. This is the actual carbon atom attached with the which is connected with the carbene. If they have the heteroatom like oxygen, sulfur, and nitrogen, then therefore they will have a good pi accepting, a good kind of resonance will be there, and therefore they will be more stable. Whereas in case of the straw carbene, you don't see any heteroatom. You don't see any heteroatom attached to the carbon. What I'm talking about the straw carbene. But Fischer carbene na, and the carbene carbon la sutti enna irukku appadina, you will actually have the you actually have the some heteroatom substituents like oxygen, sulfur will be there. But if we talk about the straw carbene, they don't have only the carbon or hydrogen will be present. Therefore, it is responsibility to know what sort of carbene. And heterocyclic carbene means it is actually two, at least the minimum requirement is one nitrogen atom should present in the one nitrogen atom should be present in the ring. When you talk about the Fischer carbene, one heteroatom should be present in the carbon atom. And when you talk about the straw carbene, there should be only carbon and hydrogen present in the carbon atom. Therefore, simply looking at the compound, we could be able to get the correct idea which carbene is it is. Okay, so again, when you're coming to the bonding nature of your triplet carbene means it actually have a pair of electron, a pair of electron present in the, I should mark it here, the pair of electron present in the carbon which can donate to the metal center. As a result, the more electron density, now you have a empty PR sigma star orbital through which the back bonding take up the electron. This is about the bonding, the pair of electron to the metal center, and we can use the pz orbital to accept the electron density. So when you do some interesting analysis among the Fischer carbene and straw carbene, the Fischer carbene actually have an additional stability because of the resonance. Look at here. Look at here. This is something called the additional uh, uh, additional resonance structure. Therefore, the Fischer carbenes are generally more stable than the straw carbene because straw carbene do not have this kind of heteroatom. Therefore, they are less stable, and therefore that is what the Fischer carbene is more stable. And this is the comparison. This is also not that much bigger. Okay, look at this. Are all example for the Fischer carbene. Look at here. In all the center metal attached only with the carbon atom. Okay, and then if you look at the metal are in lower oxidation state, and therefore we can say the metals are electron rich. The metal is electron rich, therefore it will undergo the look at all these cases, the metals are electron rich, and look at the carbon atom attached with the heteroatom like oxygen, sulfur, which is more electronegative than the carbon atom. Therefore, the electron density will be pulled toward. Therefore, the Fischer carbon is actually electron rich. Fischer carbon is electron deficient. Therefore, it will undergo nucleophilic addition reaction. Whereas in this case, the metals are electron rich. Therefore, they will undergo electrophilic addition reaction will happen. This is what we talk about. And coming to the straw carbene means we're talking about the singlet carbene. We're talking about the singlet carbene. Single carbene means the two electrons will occupy the px and py orbital. Px and py orbital. Therefore, it will form one sigma bond, another pi bond. With using the two electron, therefore it's a conventional single and double bond between the metal and carbon. And if you compare the oxidation state, most of the straw oxidation state are found to be very much high. Look at here, the molybdenum, these are the indicating the structure and the metal. So can you anyone please tell me what is the oxidation state of molybdenum in this system? Because I said very high. Very high means yellow. We will take the first example molybdenum and try to explain. The oxidation state of the molybdenum in the first compound. என்ன போறது?
Sir, +6.
+6. எதுவும் +6 சொல்றீங்க? How it is +6?
Sir, oxygen 2 oxygen இருக்கு minus.
-1 okay. அப்புறம்
Nitrogen N2 minus ligand.
okay. That is actually N2 minus. There are two negatives, therefore 2 minus. That's all correct. Good.
This straw carbene -1.
Why straw carbene has to be treated as L2, X2? Whereas Fischer carbene and N heterocyclic carbene both are L type. Whereas Fischer carbene is actually X type. Because it is actually giving one electron, not the pair. அது பேரா கொடுக்கறது இல்ல, ஒவ்வொரு எலக்ட்ரானா கொடுக்குது. அப்ப என்ன ஆகுது அப்படின்னா the bonding the bonding is actually a kind of a metal Cl. Therefore it is actually considered as an ionic bond kind of a, therefore one electron per metal, and therefore it is actually a, the answer is correct. They actually in the +6 oxidation state. If the metal is in +6 oxidation state, the density will be low. Therefore here Fischer carbene, the metal will undergo the nucleophilic attack, whereas your carbon now attached only with the only with your what I can say, only with your electron releasing group, and therefore what will happen, the metal center will be in electron rich. Therefore the carbon will be in electron rich. Therefore they will undergo the electrophilic substitution reaction. Therefore the lot of, it looks like simple, the Fischer carbene, star carbene, they look almost same when you're just simply writing, but that is not true when you coming to the reactivity and bonding. Your Fischer carbene and star carbene and endo heterocyclic carbene, I think I have a comparison here. This is also fine. Yeah. So look at, almost they have same comparison, but look at, they actually vary a lot. Actually, they vary a lot because Fischer carbene is a neutral, whereas star carbene is a X type of ligand, and all this happen here. Okay, this is about the Fischer carbene. Now, கொடுத்த compound Fischer or star carbene எப்படி கண்டுபிடிக்கலாம்? By looking at the heteroatom present in the carbon, we can say it is a the Fischer carbene. அப்படி எதுவுமே இல்லை, extra no heteroatom attached to the metal center, then we can say it is a Schrock carbene. அந்த மாதிரி நம்மளால ஈஸியா ஐடென்டிஃபை பண்ண முடியும். ஓகேங்களா? வேற டவுட் இருக்காப்பா Fischer carbene, Schrock carbene? Any doubt?
No, sir.
Okay, fine. ஒருத்தர் தான் புரியுதோ, பாக்கியெல்லாம் புரிய மாட்டேங்குதோ? நான் பேசுறது புரியலையாப்பா உங்களுக்கு எதுவும்? இது நான் வந்து குழப்பறேன் உங்களை. ஏன்பா ரொம்ப டல்லா இருக்கீங்களா இன்னைக்கு?
புரியுது
சண்டே.
இல்ல சார், அண்டர்ஸ்டாண்ட் பண்ணிக்க முடியும்.
Okay, fine. Good. Okay, good. Very good. Okay. So we can extend the strategy. If an organic compound can make a carbon-carbon triple bond, why not the metal carbon triple bond? Yes, it is possible. Instead of using carbene, we can actually say carbine. What is carbine? Carbon means it's a CH. But how there are 3 electrons are present, how these 3 electrons are arranged in the orbital, we classify as a doublet carbene and a quartet carbene. What is meant by a doublet carbene? One will be paired up, one will be singly occupied. Therefore, the other hand, we have a quadruplet carbene where all the 3 electrons are actually singly occupied. Therefore, the bonding will be here. One will be a pair of electron, other will be through the central back bonding corresponding to M double bond L. Whereas in this case, there is a there is a metal carbon triple bond carbon C. Yeah, triple bond carbon C is actually present by forming a 3 electrons are present. Metal will contribute 3 electrons each other. They will form a stable compound will be forming. If I'm generating the metal center from the Fischer carbene, we say it is a Fischer carbine. If it is taken from the if it is derived from the quartet carbine, we say it is a Schrock carbine. Exactly the same way what we discussed. This is single carbene and Fischer carbene. To be frank, Fischer carbines are very, very difficult in this. And for imagine the power of the expensive nature, cost-wise very expensive Schrock carbene. But of course, your Schrock carbene actually have a very strong catalytic activity than the Fischer carbene. Okay, this is overall summary. I think we are actually concluding the sigma donor ligand, where we talk about starting with the carbon monoxide and end with the N heterocyclic carbene and the the carbene ligand. And now we have a strong, like you have a triple bond, double bond, all can act as ligand. You can this carbon sulfide, all this can act as ligand. But water, triethoxy ether, sulfoxide, and NR3, all it won't show any pi accepting nature. They're simply considered as a sigma donor or other thing. Whereas other molecule like carbon monoxide, nitrosyl, the phosphine, the H and bromide organics can also do the can act as a organometallic ligand. And talk about the sigma donor, the pi donor, and then we have a overall summary which is acting as a sigma donor, which is acting as a the pi star accepting ligand can be identified. Okay. Yes, we have completed the sigma donor ligand. Now we may need to go for the pi donor ligand. So அதோட முடிஞ்சது actually pi donor ligand. But pi donor ligandலையும் நம்ம நிறைய எதை பத்தி பேச போறோம்னா pi back bonding பத்தி தான் பேச போறோம். As I said, the organometallics only three different type. One is the 18 electron rule talking about the stability. The other one is the pi back bonding ability and the pi accepting ability of the system. So நம்ம வந்துட்டு sorry. We actually done the whole sigma donor ligand. Now we need to discuss how the pi donor ligand has பண்ண போறோம். So சொன்ன மாதிரி மூணு கான்செப்ட் 18 electron pi accepting MO diagram. But this MO diagram, sorry, not the MO diagram, this pi accepting ability. எந்த பக்கம் pi accepting ability போதி பார்க்கறதுங்கிறதா ரொம்ப முக்கியமானது. So far we discussed in terms of the compounds IR searching frequency, how it vary, how it affect the pi accepting nature. We also talk about the pi accepting nature எப்படி கண்டுபிடிக்கணும்னு நம்ம பார்த்திருக்கோம். Similarly, we will do for the other pi donor ligand. What is pi donor ligand? The pi donor ligands are also a sigma donor ligand. The major difference is that the electron is actually, the pair of electron is actually coming from the pi orbital. The sigma pair of electron coming from the sigma orbital is called as the pi orbital, pi donor ligand, and the remaining things are exactly same. And because of the pi back bonding, what is actually happening to the olefin ligand, that and all we will discuss, because எடுத்து அப்புறம் நிறைய போய்கிட்டே இருக்கும். ஸோ அதனால நம்ம எடுக்க வேணும்னு பார்க்குறேன். ஸோ நெக்ஸ்ட் கிளாஸோட we could able to complete. We get to talk about the 2 member and then we go to the third concept called metallurgy. So next week நம்மளால வந்து organometallics நம்மளால முடிச்சிட முடியும். ஓகேங்களா? ஸோ இஸ் தேர் எனி ப்ராப்ளம்? உங்களுக்கு ஏதாவது டவுட்டு? I think last week I shared some material with some students. கொஞ்சம் பேர் கேட்டிருந்தாங்க. நான் உங்களுக்கு எல்லாத்துக்குமே நான் கொடுத்துட்டேன். யாருக்காவது மிஸ் இருந்தால் கேட்டு வாங்கிக்கோங்க. I can share the thing. And then ஏதாவது டவுட்டு ஒர்க் அவுட் பண்ணிட்டீங்களா? ப்ராப்ளம்ஸ் ஒர்க் அவுட் பண்ணி பார்க்குறீங்களா? ஏப்பா
சார்
ஒன் மினிட். கேளுங்கப்பா ஜஸ்ட்
சார் இந்த ஹைட்ரைட்ல வந்து 6 electrons 4 electrons bond போட்டீங்களா சார், எப்படி சார்?
இல்ல நான் 6 electrons சொல்ல, அதுல வந்து could able to see close it. Yes, no, I didn't say they are 6 electron. They may connect with 6 metal, 7 metal, something like that. I mean, only one hydrogen ligand will be there. It may act as a bridging ligand with 3 or 4 metal, 5 metal, 6 metal, no problem. Because hydride actually have only one ligand, only one electron. Therefore, irrespective nature of their bonding, it could able to donate only one electron. அதுதான் இங்க சொல்லியிருக்கோம். It is a அப்ப நீங்க நம்பர் ஆஃப் மெட்டல் கூட என்ன ஆகும்னா the interaction become ஒரு மாதிரி வீக்கரா தான். That is இந்த காம்பவுண்ட்ல ஆக்சுவலா we say interstitial compound தான். Interstitial compound தான், because it is actually the one hydrogen atom is actually occupying the void. ஒரு சின்ன கேப் இருந்தது, கேப்ல உட்கார்ந்துருச்சு. But using that one, it is actually interacting with the all 7 carbon atom. Therefore, actually, if you ask for a bonding, your hydrogen ligand can donate 1 electron, iridium ligand, sorry, the metal can donate 1 electron. But அதை வச்சுட்டு எல்லாம் உள்ள முடியாது. Therefore, it is actually holding. It make a bond. The bond will be relatively weaker, but therefore that can be considered as a ligand, and therefore we are considering here. And actually, it's a 1 electron donor in terms of your the neutral atom.
ஒரு இது எப்படி சார் மெட்டலோட பாண்ட் ஆகுது? ஒரு ஹைட்ரஜன்
அதுதான் இன்டராக்ஷன். இது வந்து நம்ம இந்த கேஸ் இது ஐ திங்க் இந்த ரெண்டும் உங்களுக்கு ஓரளவுக்கு ஜஸ்டிஃபை ஆயிருக்கும் நான் நம்புறேன். So it is actually like a carbon monoxide. ஹைட்ரஜன் ஆட்டத்துல அதுகிட்ட ஒரு எலக்ட்ரான் தான் இருக்கு. நீங்க ஒரு எலக்ட்ரானை எத்தனை பேர் பங்கு போட்டாலும் அதுக்கு இருக்க தானே கொடுக்க முடியும். See, when you talk about the chlorine, when it is chlorine through the negative charge one electron donor bridge பண்ணும்போது என்ன பண்றோம், இன்னொரு பேரா ஆஃப் எலக்ட்ரான் எடுத்து 3 மாத்துறோம். குளோரின்ல 1 3 5 7 3 4 different type of mode of coordination is possible. பட் இங்க வந்து ஹைட்ரஜன் லிகாண்ட் தான் H மைனஸ். H மைனஸ்ல மொத்தமே 2 எலக்ட்ரான் தான் இருக்கு இல்ல, அதனால வேற எடுக்கவே முடியாது. அப்ப போட்டிக்கு இந்த பங்குக்கு ஒரு 4-5 மெட்டல் வந்தாலும் ஹைட்ரஜனால எவ்வளவுதான் ஷேர் பண்ண முடியும், ஒன்லி ஒன் எலக்ட்ரான் கேன் பி ஷேர். அப்போ இஃப் யூ ஆஸ்க் மீ தி கொஸ்டின், அப்போ அது பாண்டா இருக்க முடியுமான்னு கேட்டா, தட் இஸ் ஆக்சுவலி பாண்ட். தி பாண்ட் இஸ் வெரி வீக். லுக் அட் ஹியர், 3 சென்டர் 2 எலக்ட்ரான். இப்ப நீங்க அந்த பிரிட்ஜிங்ல போற எலக்ட்ரான் வேணும்னா யூ நீட் அ மினிமம் 3 எலக்ட்ரான். அங்க இருக்கிறது ஒரு எலக்ட்ரான் தான். அப்படி என்ன ஃபார்ம் ஆயிருக்கும், அந்த 2 எலக்ட்ரான் வேற எங்கேயா கடன் வாங்குற மாதிரி மாறி மாறி வந்துட்டு இல்ல. Therefore it is actually bonding, but the bonding is very weak. அதான் அர்த்தம் அதுக்கு வந்து.
In case of 4 center 2 electron,
சேம் வே 3 மெட்டல் இருக்குப்பா. 3 மெட்டலோட ஒரு லிகாண்ட் லிங்க் பண்ணனா ஒவ்வொரு மெட்டலும் ஒரு எலக்ட்ரானை கொடுக்க வாய்ப்பு இருக்கு. பட் ஹைட்ரஜன் என்னதான் பண்ண முடியும், ஹைட்ரஜன் 3 பேருக்குமே சேர்த்து ஒரு மெட்டல் தான் கொடுக்க முடியும் இல்ல. அப்ப எப்படி ஒரு எப்படி ஒரு ஹைட்ரஜன் இருக்கு ஒரு எலக்ட்ரான், அது ஒழுங்கா ஒரு மெட்டல் தான் கொடுத்தாதான் நல்லா ஸ்ட்ராங் பாண்டிங் ஆயிரும். பட் அது என்ன பண்ணுது, நீ அப்படி இருக்கியா ஏன்டா ஒரு எலக்ட்ரான் தான் இருக்கா, 3 பேருமே வந்து 3 பேருமே ஷேர் பண்ணுது. தட் இஸ் வை இட் இஸ் ஆக்சுவலி 4 சென்டர் 3 எலக்ட்ரான் பாண்ட். சரி, 4 சென்டர் 2 எலக்ட்ரான் பாண்ட். H மைனஸ் 2 எலக்ட்ரான் தான் இருக்கு. அந்த 2 எலக்ட்ரானை 4 ஆட்டம் ஷேர் பண்ணா யாரு, 2 மெட்டல் 3 மெட்டல் ஒரு ஹைட்ரஜன் இல்லையா. அப்ப அந்த பாண்டிங் ஓவர்லாப் சொல்லுங்க மாலிகுலர்
போடும்போது லைக் எப்படி சார் போடுறது?
இதுக்கு நீங்க எப்படி போடணும் அப்படின்னா, யூனிட் இட் ஹஸ் a ஸ்பெஷல் பாண்டிங். இது வந்து பனானா பாண்டிங் கேள்விப்பட்டிருப்பீங்க, எஸ்பெஷலி ஹேப்பனிங் வித் டைபோரேன் இல்ல. B2H6ல உங்களுக்கு வந்து அந்த மாதிரி சாட்சி போடும், வளைச்சு போடுவோம். ஞாபகம் இருக்கா?
ஆமா சார்.
ஏன் வளைச்சு போடுறாங்க நேரா போடாம? why you draw the bond bend? ஏன் பெண்ட் பண்ணி போறீங்க?
எலக்ட்ரான் கிளவுட்.
எலக்ட்ரான் கிளவுட். சரி, எலக்ட்ரான் கிளவுட் நிறைய இருக்கும். அது எலக்ட்ரான் ரிச். பென்சீன்ல தான் எலக்ட்ரான் ரிச். இவர் போரான் இஸ் கால்ட் அஸ் எலக்ட்ரான் டெஃபிசியன்ட். அங்க இல்ல. உங்களோட சின்ன ஒரு கேள்வி கேட்கிறேன், நார்மலா சொன்னேன். ஒரு குச்சி உங்க கையில இருக்கு, அது நேரா இருந்தா ஸ்ட்ராங்கா இருக்குமா, வளைஞ்சிருந்தா ஸ்ட்ராங்கா இருக்குன்னு அர்த்தமா?
ஸ்ட்ரைட்டா தான்.
ஓகே, அப்ப நீங்க பாண்ட் நேரா போட்டீங்கன்னா அந்த பாண்ட் ஸ்ட்ராங்கா இருக்கணும். நீங்க வளைச்சி போட்டு கருவா போட்டீங்கன்னா தட் இஸ் ஆக்சுவலி வீக்லி பாண்டிங். ஏன்னா அந்த இடத்துல உங்களுக்கு வந்து 2 எலக்ட்ரான் இருந்து அங்க அந்த இடத்துல உங்களுக்கு போரான் கார்பன், அப்ப உங்களுக்கு வந்துட்டு ஆக்சுவலா வந்து மொத்தம் இங்க 4 எலக்ட்ரான் இருக்கணும். அங்க மொத்தமே 3 எலக்ட்ரான் தான், 2 எலக்ட்ரான் தான் இருக்கு. தட்ஸ் வாட் டேக் அவுட் 3 சென்டர் 2 எலக்ட்ரான். ஆக்சுவலா உங்களுக்கு 4 எலக்ட்ரான் இருக்கணும். 3 சென்டருக்குன்னா 4 பாண்ட் இருக்கணும் இல்லையா. OH2 பாருங்களேன். இப்போ OH2னா O ஹைட்ரஜன் எத்தனை 3 ஆட்டம் இருக்கு, 3 சென்டர் இருக்கு, இங்க ஒரு 2 எலக்ட்ரான் இருக்கு, இங்க எலக்ட்ரான். திஸ் இஸ் கால்ட் 3 சென்டர் 4 எலக்ட்ரான் பாண்ட். பட் டைபோரன் எப்படி இருக்கணும், இங்க ஒரு ஹைட்ரஜன், இங்க ஒரு போரான், இங்க ஒரு போரான் இப்படி இருக்கணும். பட் இந்த பாண்ட் இப்படிதான் இருக்கும். இங்க ஹைட்ரஜன் உள்ளதே மொத்தம் ஒரு எலக்ட்ரான் இல்ல, H மைனஸ் 2 எலக்ட்ரான், அவ்வளவுதான். இந்த 2 எலக்ட்ரான் எத்தனை பேர் ஷேர் பண்றாங்க, 3 போரான் ஷேர் பண்ணுது, 3 ஆட்டமும் ஷேர் பண்ணுது. தட் இஸ் இஸ் கால்ட் 3 சென்டர் 2 எலக்ட்ரான் பாண்ட். நம்ம அதை வளைச்சு போடுறோம். அந்த பாண்ட் இஸ் நாட் ஸ்ட்ராங், இட் இஸ் ஆக்சுவலி வீக். அப்ப அதே மாதிரி 3 சென்டர் 2 எலக்ட்ரான், 4 சென்டர் 2 எலக்ட்ரான், 5 சென்டர்னா the keep on the increases, the atom increases, the interaction increases, therefore weaker the bond will form. ஆக்சுவலா இதெல்லாம் பார்த்தீங்கன்னா இது பேர் இண்டஸ்ட்ரியல் காம்பவுண்ட் தான் சொல்லுவோம். மீனிங் தட் இங்க ஆனா உண்மையை சொன்னா 7 ஆட்டத்தையும் ஹைட்ரஜன் பாண்ட் ஆகி தான் இருக்கு. பட் இட் ஜஸ்ட் நீங்க ஹீட் பண்ணாலே போதும், அது அச்சுடி கேஸா வெளியே வந்துடும் இல்ல. புரியுதாப்பா? கன்வின்ஸ் ஆகலையா? ஓகேப்பா. எனிதிங் எல்ஸ்? சொல்லுங்கப்பா. சொல்லுங்கப்பா.
புரியுது சார்.
சொல்லுங்க. வேற ஓகே. வேற ஏதாவது டவுட்டுப்பா?
நோ சார்.
ஓகேப்பா. ஓகே ஃபைன். ஸோ அகைன் திருப்பி சொல்றதான், படிங்க. இஃப் யூ ஹேவ் எனி டவுட் ப்ளீஸ் கிளாரிஃபை. மேபி கவனிக்காட்டி கூட பரவாயில்ல, அட்லீஸ்ட் உங்கள்கிட்ட பிபிடி இருக்கும், பவர் பாயிண்ட் இருக்கும், எடுத்து பாருங்க, இல்லை புக்ஸ் இருக்கு, படிச்சு பாருங்க. திஸ் இஸ் அன் இம்பார்ட்டன்ட் சப்ஜெக்ட் வித் ரெஸ்பெக்ட் டு தி சிஎஸ்ஆர் அண்ட் கேட். ஸோ நமக்கு சிஎஸ்ஆர் எக்ஸாமும் கேட் எக்ஸாமும் அடுத்தடுத்து வரப்போகுது. அஃப்கோர்ஸ் ஜாம் எக்ஸாம் வரப்போகுது. ஜாம் எக்ஸாம்லேயே இப்போ நிறைய கேட்குறாங்க இந்த மாதிரி கேள்விகள்லாம். ஸோ அதனால ப்ளீஸ் ட்ரை டு ஒர்க் அவுட். இல்லை, ஒர்க் அவுட் பண்ணுறது இங்கே ரொம்ப முக்கியம். Okay, so maybe next week we could be able to complete the organometallics, the basics, the fundamental. Then we'll go for the reaction mechanism, all other stuff. Okay, so I will stop here. So if you have